Welcome to the first episode of Terrain Rendering. In this series we're going to implement most of the algorithms from the book Focus on 3D Terrain Programming by Trent Pollack using modern OpenGL. I've made many changes along the way, and I'll do my best to highlight these changes and explain the logic behind them. A terrain is obviously a very important feature in any game which takes place outdoors, and it will usually be the largest mesh in the scene. The terrain in this series is going to be represented using a grid of quads that stretches from left to right along the x-axis and into the distance along the positive z-axis. The different y values at each vertex make it look like an actual terrain. I'm using a left-handed coordinate system, but with minor tweaks you should be able to change this into a right-handed system. Each quad in this grid is divided into two triangles, and the entire structure will be maintained in its own vertex buffer. Since most of the vertices are shared between 6 triangles, we will also use an index buffer in order to avoid vertex duplication. Generating such a grid is pretty simple, but the question is, where do we get the y values for the vertices? One of the simplest solutions to this problem is to use a Heightmap. A Heightmap is a matrix, or a table, where every cell contains a height, which is the y value for the corresponding location in the grid. In this lesson, we will bring up the infrastructure for loading and rendering Heightmaps. This infrastructure will be improved with many features throughout the series. Before we get started, I'd like to give you a quick overview of the framework that we will be using. If you are familiar with my OpenGL tutorials or you have your own framework that you are comfortable with, feel free to skip ahead using the timecodes. The terrain code itself can be easily integrated into any framework. Basically, every episode in the series has its own directory with its own terraindemo.cpp file with the standard main function. The main function allocates a terrain demo application object, initializes it, and calls its run function. We will take a look at these GL calls in a minute. The terrain demo class is very simple. It has several functions to create a window using the GLFW library, configure the GLFW callback functions, and initialize a camera. There's also a function for initializing the terrain, which we're going to fill up with some code later. The run function waits until GLFW signals that the window has been closed. It calls the render scene function, which is where we're going to build up the frame. It also swaps the buffers and polls for events. Standard GLFW stuff. Right now, the render scene function only clears the back buffer. We also have 3 callback functions for handling the mouse and the keyboard. Note that you can quit the application by clicking on Q or Escape, and that the W button always toggles between wireframe and full polygon mode. The function createWindow uses a utility function called glfwinit to take care of creating the glfw context and the window. Again, standard glfw stuff. initCallback registers the 3 callback functions that we saw, and initCamera initializes the position, target vector, and perspective projection information for the camera. This is the same camera class that I've developed over the course of 3 of my OpenGL tutorials, so you should check them out if you are not familiar with that, but any camera code that you already have will probably work just as well. The class also contains private attributes for the GLFW window, the camera, and the wireframe indicator. We're going to add more attributes as we make progress. Back to the GL calls in the main function, we can see that we are setting the clear color to black and enable backface culling. The triangles will be specified in clockwise order. No special reason for that, but if you change this, make sure to fix the code which actually initializes the indices. And we also enable the depth test. If we run this right now, we should be getting a nice empty window, and we can do the first step, which is to load the Heightmap. For that, we're going to create a class called baseTerrain to store and render the Heightmap. I'm going to write the important pieces of the code except some boilerplate stuff like include files, declaring if and defs in the headers, things like that. You can find the link to the full source code in the video description. Right now this class has an empty constructor and we need a function to load the Heightmap from a file. We're going to add a protected attribute for the Heightmap itself, and for that I'm using a utility class called Array2D, which I've already created. This is a very simple wrapper for a buffer of memory, and it provides access to it as a two-dimensional array. The class is templated on the data type of the buffer, so the same code can be reused for different data types. In the constructor, we provide a number of columns and rows, and the number of bytes that we allocate is the number of rows times the columns times the size of the data type. The class provides several functions for accessing the data as either a 2D or 1D array. There are a lot of checks all over the code to make sure we are not making an invalid memory access. So our Heightmap is a 2D array of floating points. The book actually uses an 8-bit Heightmap, but I found out that floating points provides a much smoother terrain and overcomes various visual anomalies. In addition to the Heightmap, we need an attribute to store the size of the terrain. For simplicity, the terrain will be square, so the width and depth of the Heightmap are equal to the terrain size. Now let's write the function loadFromFile. Again, I'm using a utility function that I already have called readBinaryFile. This function takes the name of the file and returns a pointer to a buffer with the contents of the file. We also supply an integer parameter as a reference, and readBinaryFile will populate it with the size of the file, which is also the size of the returned buffer. Notice that I'm not doing any checks on the returned pointer because readBinaryFile will exit on any error. ReadBinaryFile is very simple. It uses fopen to open the file as binary, stat to get the file size, and fread to read the file contents into the buffer that was allocated according to the size. The file is closed and the buffer is returned to the caller. Back to loadFromFile, let's make sure the file contains a whole number of floating points. The terrain size is calculated as the square root of the file size. Don't forget to divide by the size of a float before calling square root, because that's the size of the basic element. We can now initialize the Heightmap using the terrain size as both the rows and columns of the 2D array. This constructor takes a pre-allocated buffer. Notice that the Array2D class always deallocates the buffer in the destructor, regardless of whether it was allocated internally or externally. In this case, the buffer was allocated by readBinaryFile, and it will be deallocated by Array2D. Now I'd like to make sure that the file was read correctly, so let's add a temporary call to an Array2D function called printFloat, which will print the contents of the Heightmap. Let's go back to the terrain demo class, add a base terrain as a member, and in the initTerrain function, we'll call loadFromFile using a Heightmap, which is checked into the Git repo. Let's run this, and as you can see, the contents of the file looks okay, at least in the sense that there's no evidence of garbage. Okay, we are now getting to the core of this lesson, which is to use the Heightmap in order to render a terrain. I've made a design decision to separate the management of the OpenGL stuff from the terrain. In the future, this will allow us to write a sort of a rendering backend in other APIs such as Vulkan and DirectX, while keeping a lot of the code unchanged. The OpenGL stuff will be maintained in a class with a very original name, TriangleList. This class will create and render a grid of triangles while taking their height from the Heightmap. TriangleList needs attributes for the width and depth of the grid. While the terrain is square, I decided to make this class a bit more generic to make it easier for me to reuse it in my future projects. We also need handles for the vertex array buffer, the vertex buffer, and the index buffer. If you're not familiar with these concepts, make sure to watch my OpenGL for Beginners series. The attributes are private and we need a public function to create the TriangleList. This function takes the width and depth as parameters, as well as a pointer to the terrain in order to get the heights. We also need a function to do the rendering. In the createTriangleList function, we store the depth and width, create the OpenGL state, and populate the buffers. Before we exit this function, we disconnect our VAO, vertex and index buffers from the opengl state. In the createGL state function, we allocate and bind the VAO as well as the vertex buffer. I'd like to start by simply rendering the grid of vertices as points, so let's postpone the indices for now. Next, we need to define the layout of the vertex buffer. Right now, our vertex only contains the position, but later we will also have a normal and texture coordinates, so let's define a structure called vertex with an attribute for the position. This structure has an initialization function that takes the terrain pointer, as well as the x and z coordinates. We can now enable the vertex attribute and configure it for the 3 floating points of the position. The vertex attributes will be packed together in the same buffer, so we can use the size of the vertex structure as the distance between 2 consecutive positions. I'd like to make it easier to add attributes later on, so let's define a variable for the number of floating points in the layout. The last parameter of GL vertex at3 pointer is an offset in bytes, so we need to multiply the number of floating points by the size of a float. We will also increment it by 3 to make it ready for future attributes. Okay, let's hope that the opengl state is set up correctly. The next stage is to populate the vertex buffer with the position of the vertices in the grid. We prepare a vector of vertex structures. The width and depth of the terrain represent the number of vertices along the x and z axes, respectively, so we multiply them to get the total number of vertices. The function initVertices will perform the actual population of the vector with vertex positions. Once the vector is fully populated, we call GLBufferData with the size of the vector in bytes. This value is obtained by multiplying the size of the first element in the vector by the number of elements. We also pass in the address of the first element in the vector. Let's see how to initialize the vertex positions. This is actually very simple. We perform 2 nested loops over the depth and over the width. We call initVertex on the current element in the vector and move the current index to the next element. Let's write the initVertex function. For now, we will initialize the position using the x and z coordinates and set the y to 0. We will later use the terrain for the height. All we have left is to write a render function. This requires binding the VAO and calling GLDrawArrays using GLPoints as the topology. The first vertex is 0 and the total number of vertices is the width times the height. We have a few more things to do before we can render. First, we need a couple of shaders. In the vertex shader, we declare the layout of the position. We also have a uniform for the combination of the view and projection matrices. Usually in rendering, there is also a world matrix, but our terrain is constructed directly using world coordinates. This means that I'm not going to scale, rotate, or translate it. The main function just needs to extend a position to a 4D vector and multiply it by the view projection matrix. As usual, the result goes into the GL position variable. In the fragment shader, we declare an output variable for the color. For now, let's just set it to white. Okay, we need to compile and link our shaders, and for that I will use my existing infrastructure, which is based on my technique class. This class takes care of setting up the shaders and providing access to their uniform variables. It was also described in my OpenGL for Beginners series. I already prepared a terrain technique class to bring up those 2 shaders, so you can check the code later. What we need to do next is add the TriangleList and terrain technique as members in the terrain. We also need a couple of functions to initialize and render the terrain. In addition, I'd like to factor out the file loading stuff from the load from file function because we need to do more stuff there. The initTerrain function just needs to call init on the terrain technique member. This will compile and link the shaders. Load from file now calls load Heightmap file and then create TriangleList. The last change in this file is the render function. It takes the camera as a parameter and extracts the view projection matrix from it. As I said, if you have a working camera implementation, you should be able to use it to generate this matrix. Next, we enable the terrain technique. This simply calls GLUseProgram using the shader program handle. And finally, we call render on the TriangleList member. The very last thing that we need to do is to call the terrain render function from render scene. Okay, if everything was done correctly, we should be getting a nice point grid. Now let's use the Heightmap. The TriangleList class will access the Heightmap information by calling getHeight using the x and z coordinates. We just need to pass the parameters to the array2d get function. It will verify that the parameters are valid and fetch the value from the corresponding location in the 2D array. Now let's go to the init vertex function and get the y value by calling getHeight on the terrain object. We should now get a nice slope for our terrain. Alright, with a few changes, we should be able to turn this point grid into a triangle grid. First of all, let's generate a handle for the index buffer and bind it to the GLElement buffer target. Theoretically, we don't really need vertex indices here. We can continue using GLDraw arrays and render triangles, but we will need the indices when we get to normal vector generation, so it's better to get the infrastructure working right now. Let's prepare a vector for the indices. How many indices do we need? Think about the point grid as a grid of quads. The number of quads along the two axes is the number of vertices on each axis minus 1. Each quad has two triangles, so we calculate the number of quads and multiply it by 6 to get the total number of indices. The indices will be populated by the initIndices function, and after that, we do a second call to GLBufferData to upload the indices into the index buffer. Generating the indices is just a bit more complex than the vertices. We do the same nested loop, but this time we stop one vertex before the end because we are actually processing quads and not independent vertices. For each quad, we calculate the index of the four corners. The basic formula is to multiply the current z by the width and add the x. The other three corners are calculated by adding an extra vertex to one of the axes or both. We can now generate the two triangles. First the so-called top left and then the bottom right. The last change is in the render function. We change GLDraw arrays to GLDraw elements and used GL triangles as the topology instead of GL points. The number of indices is exactly the same as before. Okay, let's run this, and as you can see, it's a bit difficult to tell what's going on, so let's make the color dependent on the height, because higher places are usually more exposed to light. We add an output color vector to the vertex shader, and set all components to the y-coordinate of the position. Now we need this to go from 0 to 1, and I just happen to know that the maximum value in this height map is 200, so let's divide y by 200 in order to normalize it. In the Fragment shader, we add an input vector for the color, and we copy it into the output variable fragColor. Alright, much better. Now I'd like to point out a possible deficiency in the current design. You see, the triangles are very small, and the only way to get a larger terrain is by using a larger height map. This is because the vertices, specifically the x and z, are generated using integer numbers. I'd like to introduce a concept called world scale, which allows us to scale the x and z up or down. We can easily do this in the vertex shader using a uniform variable, but since this scaling factor is known up front, it's better to simply combine it directly in the vertex buffer and just forget about it. So let's add a private variable to base terrain called world scale, which by default is 1. We provide it as a parameter to the initTerrain function, and we also need a getter function for it. And now the initVertex function can fetch the world scale from the terrain and multiply it by the x and z. Let's try a world scale of 4, and it looks very nice. Okay, we've made good progress. In the next video, we will learn the first out of 2 algorithms to procedurally generate the height map, so you can start creating terrains on your own. Thank you for watching, and I hope to see you in the next episode of Terrain Rendering.